Hello everyone. So now we come to the first oral session, and let's introduce Hunar Batra, who is a PhD student from University of Oxford. And today I will give a talk about spatial thinking, a reinforced 3D reasoning in multimodal LMs for spatial rewards. Let's give a thanks to Hunar.
Thank you for the introduction. Today I will be presenting our recent works on spatial thinker models that are spatial reasoning VLMs trained with reinforcement learning to generate reasonings grounded in scene graphs and trained with our synthetic spatial VQA dataset. This work is a collaboration between VLAA Lab at UC Santa Cruz and the Pixel Lab at Oxford. So first, starting out with the motivation for this work, in spite of achieving remarkable performance in a couple of vision language tasks, vision language models still struggle with spatial understanding abilities, especially in the 3D domains, which requires the models to capture geometry, structure, and relations beyond simple 2D projections. This is also mainly due to lack of 3D spatial knowledge in these models' training process. To fix this, a couple of works like Spatial VLM and Spatial RGPT have proposed a synthetic 3D VQA generation pipeline. However, these methods are very data intensive and rely on millions to even billions of samples for training models to improve spatial understanding abilities. Some of the recent works have also proposed using reinforcement learning, specifically GRPO and other variants, for post-training VLMs for spatial understanding. However, these approaches provide sparse guidance to the model with simple rewards consisting of format and accuracy, or with just a couple of additional basic rewards related to the captions. Another motivation for our work is how scene graphs are used in existing works as an intermediary pre-processing step for VQA generation instead of having them integrated within the visual thinking process of models. And in our work, we hypothesized that in order to advance vision language models towards human level visual reasoning, we need to train them to first observe and localize scenes, generate a mental imagery via simulation of the relevant scene subgraph, having an understanding of the scene and the 3D relations, followed by reasoning and then generating the final answer. And this is also in lines with how humans in general have a rough idea of 3D relations between objects instead of the exact coordinates. And the use of scene graphs as a visual thinking step here allows us to achieve improved spatial visual reasoning in models. And with this, we introduce the SpatialThinker series of models, which have been trained with on-policy RL with a dense spatial reward design that we propose, and a high-quality synthetic spatial data generation pipeline with which we yield a training data set with 7,000 samples that we use to train these models to perceive, localize, visualize, and think. And overall, with our training, the models have much improved spatial reasoning across multiple tasks, covering 2D and 3D spatial relations, depth, orientation, counting tasks, distance, multi-object visual reasoning, and across spatial benchmarks and generic visual question answering benchmarks. So for training the SpatialThinker model, specifically we make use of on-policy reinforcement learning using the GRPO, Group Relative Policy Optimization algorithm, with which we first sample n different rollouts, which are rewarded based on our dense reward function. And based on that, the group advantages are computed, and following that, the gradient updates. And along with this, we also minimize the KL divergence with the reference model, which is the base model here. Specifically, we post-train Quen 2.5 VL, 3B and 7B models. So one of the core contributions of this work is the multi-objective reward design that we introduce. So our reward modeling process first consists of using the Hungarian algorithm for bipartite matching to match the predicted objects with the ground truth scene graphs that we have. And for this, first we have the format reward to check if the entire generated reasoning is within the specified format, and if the generated scene graph is a valid JSON or not. And we also have the accuracy reward, which is typically used for the outcome rewards. And something that we add in here is the count reward, which is something that we add because when we add in the spatial reward, something that we notice is that the models end up reward hacking by generating bogus objects and the B-box coordinates in order to maximize the spatial reward, and hence we end up adding the count penalty here. And another thing that we have here is that we have a priority ordering for the rewards. That is, we use lexicographic gating for these 4 rewards that we have, and we train the models to first perfect the format reward, and only then they are rewarded the count and the accuracy rewards. And the spatial reward is again gated by the accuracy reward, because we only want to provide the model with the process intermediary rewards if the final outcome reward is correct, and so that we're not really providing it any incorrect intermediary process rewards in the process. So this is our data construction pipeline, which is another core contribution of our works that we've introduced here. Specifically here, we use the visual genome dataset to get the ground truth images and scene graph pairs. And we augment the original visual genome dataset with additional 34 spatial relations, which cover distance, size, orientation, containment, to enrich the relational vocabulary of the existing visual genome dataset, which originally includes about 50 different predicates. And each question-answer pair is generated using Claude 4 Sonnet and rated by difficulty and quality. And further, we also apply a region of interest scene graph filtering, which is one of the important steps, because when we first ended up training the models and rewarding them for the entire scene graph of the image, we found that the models were actually overfitting when we were trying to supervise this across each and every object. So that's when we end up doing a region of interest scene graph filtering based on the question. We only keep the objects and the relevant relations between those as the ground truth scene graph, and we call this the scene subgraph. And then further, finally, we apply a data filtering with GPT-4o as the verifier model to only retain the high quality samples. And finally, we get a data set of 7,000 samples. And this entire data generation pipeline can further be scaled up to generate a maximum of 108K VQA samples, which is the limitation of visual genome dataset. Here are some examples of the dataset where we cover questions across 9 different categories, covering spatial relations, reach, existence of objects, depth-related questions, instance location-based questions, scale-based questions, distance, orientation, and count. So first, starting with the performance of SpatialThinker models on the 2D and 3D spatial VQA tasks, covering 3D SR bench, CV bench, Blink spatial, and depth, MMVP spatial, Reasoner eval, and spatial bench. Across all of these, the SpatialThinker models improve over the open sourced generic and generalist and spatial multimodal models for across all of these data sets, and specifically for 3D SR bench, CV bench 2D, and MMVP, we also improve over GPT-4o. Further, we also test our models on generic visual question answering benchmarks, some real world benchmarks like real world QA, MME real world, and robotics tasks like robospatial and a hallucination benchmark, hallusion bench, to see how the models end up generalizing to generic VQA tasks. And we see a similar pattern here as well, where our models are improving over the open sourced multimodal models, and on some of the benchmarks like MM-star, V-star bench, and robospatial, we further improve over proprietary models like GPT-4o and Claude 3.5 Sonnet. Some of the other interesting insights include that training models with reinforcement learning with a dense reward function outperforms vanilla GRPO training, which includes a simple sparse reward consisting of only format and accuracy, by about 3.2% across all 12 benchmarks that we test over. And compared to SFT, we improve over about 6% for our 7B models. And further, we see that dense rewards also enable improved out of distribution generalization, which is about 1.6 times better than vanilla GRPO here for our case. We also put the test on some abstract reasoning tasks like the ability of SpatialThinker to generalize across Lego puzzles, multi-view tasks consisting of VQA with multiple images. And we see a similar performance here, almost close to GPT-4o in Blink multi-view and outperforming the open sourced and other proprietary model baselines on these tasks. Here we have a reward design ablation. So initially, the most naive reward here would be having format and accuracy rewards. So initially, when we end up adding the spatial reward, it leads to a reduction in about 50% in the accuracy, which is something that we notice that the model actually ends up overfitting, as it was reward hacking without having a count penalty. And that's when we end up adding a count penalty here, which somewhat does recover most of the performance. And further, when we add in the region of interest filtering for the scene graphs and add in the lexicographic gating, the priority ordering that we have for the rewards, that ends up giving about a 2% increase over the basic reward design. And further, when we filter out our data set to only retain the high quality samples, we see a further boost of about 11%. That is a total of 13% boost over the base reward design here. And below, we also have the training curves for across different rewards that we train the model with, and that is format, accuracy, count, and spatial. And all of it demonstrates consistent improvement, reflecting stable learning under our lexicographic gated multi-objective reward structure. So the key contributions of our work include that we propose SpatialThinker models here, the first multimodal models integrated with scene graph-based reasoning process with reinforcement learning for improving over in-domain and out-domain spatial and visual question answering tasks. And these models have only been trained with 7,000 samples compared to other models that are usually post-trained with millions to hundreds of thousands of samples. And we also introduce STVQA 7K, which is our high-quality spatial VQA dataset grounded in scene graphs, along with a scalable data generation pipeline that can be scaled up to a maximum of 108K samples. And we design a dense reward that guides regionally focused spatial understanding in models, achieving superior in and out of distribution generalization across tasks, and outperforming conventional reinforcement learning and supervised fine-tuning baselines, open source, generalist, and spatial multimodal models, and proprietary models on a couple of tasks. Thank you. Please let me know.
Time limitation, we only can ask one question. Any question? Okay.
Thank you, Hunar. My quick question is, how do you provide the the scene graph that you generate? Is that with another model, or do you use that part of the pipeline? Like, do you generate that from the LLM, basically?
Yes, so SpatialThinker models would first generate a description of the image, and then it would generate an entire scene graph as a JSON object, including objects and relations between the relevant objects.
And you provide that as an additional context to the model for prediction.
You could do that. You could definitely add that as an external context as well. But the models have been trained to generate the scene graph itself too.
Okay.
And then reason based on the scene graph generation.
Okay. Thank you.
Thanks for that again.
Thank you.